What is quantum physics? Why should we care about knowing what is quantum physics? Do we need to know what quantum physics is? How does quantum physics affect our daily lives? Quantum physics is the physics of the microscopic world, the world of molecules, atoms, and subatomic particles. It is a branch of physics that was born in the early decades of the 20th century, with its seeds germinating in the late decades of the 19th century. Quantum physics was born out of a mixture of failure to understand certain experiments, and also out of nonsense results when applying classical physics to atoms. Yes, physicists were already familiar with the notion that matter is composed of microscopic packets, the atoms. This notion was initially put forth by the Greek philosopher Democritus, who postulated that everything is built from atoms and the void. Later on, chemists starting in the 18th century with English chemist John Dalton, and after carefully studying chemical reactions and the proportions of reagents that go in and the proportions of the resultant chemicals, correctly inferred that matter is built of individual packets, which he called atoms. Dmitri Mendeleev in the 19th century classified atoms by their chemical properties and arranged them into the periodic table of elements that we are familiar with today. We will see as we go on with our story that the chemical properties of atoms are a direct consequence of quantum physics. Physicists knew that matter is overall neutral, made up of equal positive and negative charges. So after verifying that matter is made up of atoms, experiments focused on understanding the architecture of the atom, basically understanding how the negative, electrons, and positive charges, protons, are arranged in atoms. Enter the New Zealander physicist Ernest Rutherford in the first decade of the 20th century, who shot alpha particles, helium atoms that have lost their two electrons, into thin gold foil. Rutherford observed that the alpha particles, positively charged, were deflected from positively charged point particles of much higher charge. The picture became clear now. Atoms are made up of dense positively charged nuclei surrounded by orbiting negatively charged electrons. All this is fine and nice and a source of confidence, so much so that many physicists at the beginning of the 20th century were predicting the death of physics. Their opinion went something along these lines. It's only a matter of a few years when we know all that we need to know about the fundamental physics of nature. We know everything. It's now just a matter of applying our physics to the world around us. And that is exactly what they did. But nasty surprises awaited them. Just a decade before Rutherford conducted his experiments, German physicist Max Planck was studying radiation emitted by the so-called black body. In physics, a black body is an object whose peak emission wavelength, or in other words, color, is related to its temperature. Imagine a piece of iron that you throw in a fire. As it gets hotter, it first glows red, long wavelength, and when it gets even hotter, it glows even brighter, but its color will become blue, short wavelength. This piece of glowing piece of iron is referred to physicists as black body. What Planck was pondering was what happens if one were to increase the temperature of a black body even further. The relevant physics known at the time, thermodynamics, predicted that the black body should grow yet brighter but in the ultraviolet. The color of the black body should not only shift towards shorter and shorter wavelengths, but its brightness should become increasingly higher very fast, so that it reaches infinity. But this is nonsense. How can heating an object, basically pumping a finite amount of energy into it, make it emit an infinite amount of energy? This is forbidden by the law of conservation of energy. Planck's success was postulating that radiation, or light, is quantized in individual packets of energy called photons. The energy carried by each photon is inversely proportional to the wavelength of the radiation, with the constant of proportionality now called Planck's constant. None other than the Albert Einstein used this result to describe the photoelectric effect experiment, another important experiment of quantum physics, for which he later won the Nobel Prize. Other physicists in the early decades of the 20th century applied their physics known to them at the time, classical mechanics and electromagnetism, to the simplest of atoms, the hydrogen atom, one electron orbiting a single proton. Let us put our physics hats on. Classical mechanics says that an object orbiting a center must experience centrifugal acceleration. Electromagnetism says that an accelerating charge must give off radiation, energy. Now let us put one and one together. The electron, a charged particle, as it orbits the proton in the hydrogen atom, will experience acceleration, so it must radiate. So far, so good. However, and here comes the nasty surprise, the radiation emitted by the electron will steal away its energy, making its orbit decrease and spiral towards the proton in a fraction of a fraction of a fraction of a second. So basically, classical physics predicts that no atoms should exist, and by consequence, we too should not exist. This nonsense result was a slap in the face of early 20th century physicists that not all is well with physics, or at the least, there must be something over and beyond the classical physics known till then. Classical mechanics, thermodynamics, electromagnetism, and optics. This new physics became known as quantum physics. Its cornerstone is that all physics quantities that could be observed, the so-called observables, are all quantized. That is, they come in individual, discrete units instead of taking on a continuum of values as in classical physics. Faced with the above, atoms should not exist debacle, Danish physicist Niels Bohr proposed in the second decade of the 20th century his toy model of the hydrogen atom. He postulated that the existence of stationary orbits in which the electron, if it satisfies a certain condition, does not radiate its energy away. That condition is related to its orbital angular momentum, and it dictates that the orbital angular momentum of the electron in this orbit must be a definite multiple of Planck's constant. This toy model was able to explain to a high degree the spectrum of emission of hydrogen atoms observed in the lab. Such work of theory and experiment going hand in hand was the way in which quantum physics was built. Moreover, quantum physics was a group effort in which nearly all physicists working at the time contributed to the endeavor, some more than others, of course. This kind of work continued well into the 20th century, in which quantum theory was fully developed and compared against experiment. Of course, needless to say, experiment, which is science truthometer, agreed with the predictions of quantum physics. Quantum theory is the most successful theory in physics. It has also spawned new fields, material science, think smaller and more power computer chips, LED TVs, solar photovoltaic cells, etc. Nuclear physics, think nuclear power and nuclear medicine, and particle physics, theory to describe the subatomic world and related to how the universe came to exist. See other Insane Curiosity videos to learn more. Quantum theory at the utilitarian level is very powerful and leads to practical results that permeate our everyday lives. However, problems with quantum theory sprung up from the very beginning. These problems are at the interpretation level. How do you interpret the story told by the equations? Keep in mind that the equations themselves are correct and self-consistent. They give specific, well-defined predictions that turn out to be correct when tested experimentally. The problems arise when you try to understand the equations. Niels Bohr remains to this day one of the giants of quantum physics and the father of the most intriguing interpretations of quantum physics. An interpretation so bizarre, but also undeniably true, that it gave Albert Einstein many a headache. This interpretation is known as the Copenhagen interpretation. In a nutshell, the Copenhagen interpretation stipulates that if I don't see you, then you don't exist. At the fundamental level, it states that reality depends on the observer. The role of the observer is paramount in quantum physics. The observer and the act of measurement, such as seeing, itself affects the outcome of the experiment. The reason for this is relatively easy to understand. Imagine going into a dark room holding an unlit flashlight. Turning the flashlight on will shoot photons from it to an object in the room, a chair for example. These photons bounce on the chair back to your eye, and that's how you see the chair. Now, the energy carried by the photon is very small compared to the energy that could move the chair, and the chair remains in place. So the active measurement here did not change our system, the chair. Now imagine that instead of a flashlight, you have a gun that shoots golf balls at very high speeds. You go into the room and start spraying with fast golf balls. 1 or 2 golf balls are probably going to hit the chair and may also probably move it too. From the sound of the golf balls crashing on the chair, you will know where the chair was located. But now the new position of the chair becomes unknown. Therefore, the active measurement here changed the system. Of course, in quantum physics, all systems are microscopic, and the measurement tools are also microscopic, leading measurements to messing with the system. The Copenhagen interpretation takes this notion to the max and says that the very active measurement makes a system exist. One might be tempted to say, this is just an interpretation, and it needs not be correct. However, recent experiments done at top quantum optics labs strongly suggest that the Copenhagen interpretation is correct. A very graphic illustration of the apparent absurdity of quantum physics and the Copenhagen interpretation is the Schrödinger cat paradox. In this famous experiment, named after Irish-Austrian physicist Erwin Schrödinger, a cat is put in a closed box with a sealed vial of poison. A radioactive source might decay at random and emit a radioactive particle that would break the seal, thus killing the cat. To an outside observer, the cat has a 50-50 chance of being dead or alive. The way this is expressed in quantum physics formulas, the so-called state function will assign equal weights to the cat being dead or alive. A physicist can do all calculations required and compare 2 experiments and all will be fine. But when the physicist tries to interpret the state function formula, all hell breaks loose. The equation seems to be saying that the cat is dead and alive at the same time. But remember, who determines the truth? It is the act of observation itself, the measurement. The observer will have to open the box to determine whether the cat is alive or dead. Another weird aspect of quantum physics is the so-called particle-wave duality, or the complementarity principle. In our macroscopic world, matter behaves like particles. The ball is here, the bike is there, and light behaves like a wave, cause of the rainbow seen on a DVD's data surface. In the microscopic world governed by quantum physics, an entity, matter or light, will behave as a particle or a wave, depending on the experiment. More support to the Copenhagen interpretation above. French physicist Louis de Broglie, author of probably the shortest doctoral thesis in physics, in which he presented the smallest formula that would later win him a Nobel Prize in Physics, proposed in that same thesis in the 1920s that a particle with a given value of linear momentum, basically mass multiplied by velocity, will have the wavelength of its complementary wave inversely proportional to its momentum. The constant of proportionality is Planck's constant yet again. Experiments done on electrons show that they behave like a wave upon passing through very narrow slits, a behavior seen for light also. Albert Einstein successfully explained the photoelectric effect mentioned before by invoking the particle nature of light. In that experiment, light will behave like small particles, photons. What is quantum mechanics? Explained. You are currently facing one of the most important equations of all time. It is called the Schrödinger wave equation. Let me explain why it is so beautiful. First of all, as you can see, it's really simple. Usually in the physics world, simple and elegant formulas are the most important ones. Even Einstein had this strong belief that the world and the universe could have been described by means of some cute formulas. A well-built theory is usually visually good in terms of equations. As Einstein himself said, it can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible, without having to surrender the adequate representation of a single datum of experience. Just think about it. It's like when you want to express your emotions. Sometimes you don't think too much about them. Your words come out of your mouth and you produce a messy cascade of words. Your interlocutor can still understand what you are saying, but it is kind of difficult to follow your thoughts. But if you write your thoughts on paper, you'll probably find a better way to express them, a more efficient and concise way. This also holds for physics theories. We could have good ones, but some of them are just more elegant than others. Of course, this is a hard job, and our scientific inability to simplify is something we should always accept. But besides its formal beauty,
the Schrödinger equation tells us something more. It is the starting point for the understanding of quantum mechanics. What is it? I could start and end this video by saying that quantum mechanics is the study of very small things, but you would be very disappointed then. So I will try to tell you something more. First of all, for very small things, we mean we are interested in stuff that exists in the real world, but has atomic scale dimensions. We are talking about atoms and subatomic particles. We can say quantum mechanics deals with the atomic and subatomic world, and if you take a lot of particles, you have the macroscopic world. The macroscopic one is the world you and me are used to. In everyday life, we have to deal with macroscopic objects. Your mocha is a macroscopic object. However, it is made of atomic and subatomic particles. Now, the macroscopic world is well described by classical physics. For example, Newton gave us some laws that fit well what we observe in the everyday life. Classical physics can help us understand why the Earth orbits around the Sun. Why do we have seasons, how planes fly, and much more. So it is really useful. But at a certain point, at the end of the 19th and the beginning of the 20th century, scientists realized that something was missing. When they decided to study the atomic and subatomic world, they found classical physics didn't work anymore. They needed another approach. This was a huge issue, a problem that needed to be solved. In fact, physics is no more physics if it can't describe reality. The desire to resolve inconsistencies between observed phenomena and classical theory led to two major revolutions in physics that created a shift in the original scientific paradigm: the theory of relativity and the development of quantum mechanics. The most important result is that light behaves in some aspects like particles and in others like waves. I know what you're thinking. No way. And that's pretty much the same thing physicians were thinking when they first approached the undiscovered world of quantum mechanics. Let me explain it better. Matter, the stuff of the universe, consists of particles such as electrons and atoms, but it also exhibits wave-like behavior. This phenomena has been verified not only for elementary particles, but also for compound particles like atoms and even molecules. For macroscopic particles, because of their extremely short wavelengths, wave properties usually cannot be detected. Although the use of wave-particle duality has worked well in physics, the meaning or interpretation has not been satisfactorily resolved. Bohr called it the duality paradox and regarded it as a fundamental or metaphysical fact of nature. A given kind of quantum object will exhibit sometimes wave, sometimes a particle character in respectively different physical settings. He saw such duality as one aspect of the concept of complementarity. Talking about this wave-particle duality, Einstein said, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." One of the most famous experiments that allowed scientists to understand the dual nature of matter was the double-slit experiment. It demonstrates with unparalleled strangeness that little particles of matter have something of a wave about them, and suggests that the very act of observing a particle has a dramatic effect on its behavior. To start off, imagine a wall with two slits in it. Imagine throwing tennis balls at the wall. Some will bounce off the wall, but some will travel through the slits. If there's another wall behind the first, the tennis balls that have traveled through the slits will hit it. If you mark all the spots where a ball has hit the second wall, what do you expect to see? That's right, two strips of marks roughly the same shape as the slits. In the image below, the first wall is shown from the top and the second wall is shown from the front. Now imagine a light at a wall with two slits. As the wave passes through both slits, it essentially splits into two new waves, each spreading out from the slits. These two waves interact with each other, and they are said to interfere with each other. The interference could be disruptive or constructive, and in the first case, they will cancel each other out. In the second case, they will reinforce each other, giving spots with the brightest lights. So when the light meets a second wall placed behind the first, you will see a stripy pattern called an interference pattern. Now, if you do the same thing with a beam of electrons, you would expect to see two rectangular strips on the second wall, as with the tennis balls, because they are particles. But what you actually see is that the spots where electrons hit replicate the interference pattern, form a wave. As you can see, this experiment suggests that what we call particles, such as electrons, somehow combine characteristics of particles and characteristics of waves. And this is the real essence of the quantum world. Basically, everything can be described or associated with a so-called wave function. In physics, we usually indicate a wave function by means of the Greek letter psi. And if you remember, the psi function appears in Schrödinger's equation. In quantum mechanics, the Schrödinger equation is a fundamental equation that determines the temporal evolution of the state of a system. For example, of a particle, an atom, or a molecule. When it comes to quantum mechanics, intuition is no more present. For example, if you hold a ball, you will notice it has some mass because of its weight. You can feel its weight, and if you take something heavier, you will notice. It is just something very intuitive, and the classical physics world is built upon this kind of intuition. However, when it comes to quantum physics, things get more complex, and we soon realize we can't predict exactly what is going to happen to the motion of a ball, for example. Or we can't really tell, for example, if a cat is black or white. One has to imagine reality as a set of possible configurations, and you don't know a priori which configuration is going to be chosen. We can tell that there is a certain probability associated with each configuration. Only when we make measurements, we can see the chosen configuration, which we call state. Let's go back to the cat. Let's suppose you want to pet him. We have a cat, but we don't know if it's black or white or whatever color. Quantum mechanics essentially states that the only way for us to know which color the cat is to measure it, and we do so by applying some mathematical objects to the state of the cat, which is called operators. You have a wave function, a state, which in this case is the color of the cat. You apply an operator. You get the result black, white, or whatever. If you repeat the experiment a high number of times, you will end up with a distribution probability of colors. And this distribution will have a peak on one color, and that will indeed be the color of the cat you are wanting to pet. One of the big requirements of quantum mechanics is, of course, the description of macroscopic reality. In the big number of atoms limit, quantum mechanics should reproduce the macroscopic world. That is, putting in the crassest possible terms, if you see the cat is white, quantum operators applied to the color configuration should mainly give the white result. Many aspects of quantum mechanics are counterintuitive and can seem paradoxical because they describe behavior quite different from that seen at larger scales. Do you know what quantum physicist Richard Feynman said about quantum physics? Feynman said quantum physics deals with nature as she is absurd. For example, the uncertainty principle of quantum mechanics means that the more closely one pins down one measurement, such as the position of a particle, the less accurate another complementary measurement pertaining to the same particle, such as its speed, must become. And if you know very well the position of a particle, you will lose a lot of information about its speed, and vice versa. You know very well the velocity of a particle, you will keep losing track of it. Another example is entanglement, in which a measurement of any two-valued state of a particle, such as light polarized up or down, made on either of two entangled particles that are very far apart, causes a subsequent measurement on the other particle to always be the other of the two values, such as polarized in the opposite direction. Quantum mechanics teaches us an important thing about nature. Its description is essentially probabilistic. Before quantum mechanics, we were used to thinking that the world is governed by some given laws that give precise results. You act, you get precise results, and every action is followed by a reaction that seems to be predictable. Instead, nature doesn't work like that. The probability of an event, for example, where on the screen a particle shows up in the double-slit experiment, is related to the square of the absolute value of the amplitude of its wave function. We can just say, for example, that we have an 80% chance that we'll find the particle in a given position interval, but we will know where it is only when we will measure it. Another important thing quantum mechanics tells us is that it is not possible to know the values of all the properties of a system at the same time. This is, of course, due to the uncertainty principle we discussed before. Last but not least, we know that quantum mechanics is a good theory, because even if it studies the very small things, it closely approximates the classical description of nature in the case of large systems. Well, I guess that's all for today.